All right. Well, we're couple minutes past the hour, so we can go ahead and get started. So thanks everyone for coming for what I hope is a very interesting talk from Dr. Wang. We'll see if he delivers. First, I'd like to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we're grateful to have the opportunity to work on this land. So just in case you're not familiar with the Temerty Center for AI Research and Education in Medicine, you don't have to call it that. You can call it T-CAIREM, which is what we all call it. It was founded because of a generous donation from the Temerty family. And basically, it's an interdepartmental center and trying to act as a sort of a focal point for collaboration among healthcare providers, among researchers, computer scientists, engineers, statistician, industry, all this stuff. And we're all trying to make healthcare a bit better through this thing you might have heard of called AI. It's gotten a little bit popular in the last few years. Quick mention that this event is CPD accredited. So if you want to get your credit, then don't forget to complete the evaluation form, and don't forget to put your name and your email on the evaluation form, otherwise you're kind of toast. We'll have a Q&A box, which you can put questions in. Just throw the questions in throughout the lecture. I'll be reading through them, I'll keep track of them, and I'll pick all the good ones, so don't be scared to ask any and all questions, and we'll be sure to make time for them at the end. So with that, I will welcome Dr. Wang. Dr. Wang is a tenure-track assistant professor at the Department of Laboratory Medicine and Pathobiology, or LMP, and the Department of Computer Science at the University of Toronto. He holds a CFAR AI chair at the Vector Institute, and he's T-CAIREM's inaugural Temerty professor in AI research and education in medicine. And he also leads the AI team for the Peter Monk Cardiac Center at UHN. So Dr. Wang obtained his PhD from the Department of Computer Science at Stanford University. He has extensive industrial research experience at many leading companies such as Illumina and Genentech. His PhD work covered statistical methods for solving problems in computational biology. There was an emphasis on integrative cancer analysis and single cell analysis as well. So Wang's long-term research goals right now are to aim to develop an integrative and interpretable machine learning algorithm or various algorithms that can help clinicians with predictive models and decision support, and really help tailor patients' care to their unique clinical and genomic traits. So with that, welcome, Bo. Very excited to hear what you have to say today.
Thank you, Alistair. Thank you for the invitation and also introduction. Let me share screen. All right. All right. Can you see the full slide?
It looks great.
It looks great. Yep.
Awesome. Great. All right. Hello, everyone. Today I'm going to talk about the title is Opportunities and Challenges of Artificial Intelligence for Organ Transplantations. So before we start, I want to provide a full disclosure that I'm an inventor of patents related to some of the presented work. So that means don't trust everything I say. And also, I'm not a medical doctor or clinician, so all the medical and clinical related knowledge I present here is through learning from my clinical collaborators. So if I say something wrong, please don't blame me. All right, so the outline for the talk will be 3 parts. First, I will give a brief introduction of artificial intelligence for organ transplantations. And then I will present you with 2 use cases. The first one is to use AI for advanced organ assessment during EVLP. The other one is AI for long-term mortality risk stratification for liver transplantation recipients. And the last, I will walk you through some of the challenges I face for this type of research and some of the future work. All right, so we talk about artificial intelligence a lot. So, but what is AI? Right? If we ask this question 10 years ago, the first thing appearing in many people's mind is something like this. However, in reality, AI is much less cooler. Instead of threatening people's life like alien, AI is actually helping improve people's daily life. For instance, it has been widely used in smartphones to understand our voice speeches, or it is used in autonomous driving cars to free tired drivers. AI, like no other, has stricken our life like a storm. But one may wonder, what makes AI so successful? My solution to you is very simple. I summarized as ABCD with the analogy of a sports car. So if we think of AI as a sports car, to make the car run really fast, you need great wheels, strong engine, articulate steering, and sufficient oil. So same thing applies to artificial intelligence project. We need these 4 components as well. Here, algorithms are the engine. Business is the steering wheel. Computing is 4 wheels. And last, data is the new oil. And these same 4 components apply to AI applications to organ transplants as well. And I will use the next few slides to walk you through these 4 elements one by one with specific focus on organ transplant. So algorithms. So in a more academic setting, AI is a very wide concept in which machine learning is really a subset of AI. And further, deep learning, the very algorithm behind all the hype of AI, is just a subset of machine learning. So what is deep learning? Deep learning is an algorithm that bases on multi-layered neural networks, which I shown on the right. Neural networks in which you have a bunch of artificial neurons that can be set on and off, and there are connections between neurons. The cool thing about deep learning is that it can automatically adjust these millions of weights by being shown lots of real-world examples. This type of training algorithm has shown great success in many real-world applications. Although multi-layer neural networks paves the foundations for many deep learning algorithms, different models with different architectures have been tailored with respect to certain specific input modalities. For example, when it comes to image analysis, we use a specific type of neural network called convolutional neural network. This algorithm is extremely powerful to capture spatial information within an image. If you open your smartphone now and want to take a selfie, and this algorithm is being used to detect your face. The same algorithm has been widely used in analyzing medical images, including MRI, CT scan, and pathology images. And images or clinical variables most of the time are static. However, in medical fields such as organ transplant, we see dynamic or temporal signals all the time. For example, the ICU monitor readings, patients' ECG signals, or post-transplant follow-ups. When we deal with this type of dynamic inputs with temporal information, very often we use a type of neural network called recurrent neural network. The beauty of recurrent neural network is that it has a memory mechanism, mimicking how human brain memorize things. If you have an iPhone and you want to have some fun with Siri now, this algorithm is being used to understand your voice. All right, so we skip B because that's the most exciting. I save it for the last. Let's talk about C for now. So C, computing. What is the computing platforms of AI? So computing hardwares in these days are mostly the following 4 types. Among these 4 types, GPU is the most powerful and serve as the most important hardware for AI. However, it is a clear trend that the rest of low power devices, especially CPU, ASIC, will occupy more and more importance in the near future. And this is important because in many real world healthcare settings, we cannot always afford GPUs to analyze medical data and provide real-time predictions. Therefore, we need to pay attention to making our AI algorithm efficient to utilize some low power devices, which are common in clinic. And recently, we also see an increased use of cloud as a platform to train your AI models and also analyze medical data. certainly there is some concern regarding uploading medical data into cloud, but many cloud providers such as Microsoft has been really closely working with regulators and hospital IT departments to make sure the medical data is stored in a safe manner. Okay, let's look at the data, the new oil for AI. Without no doubt, we are entering an era with ever-growing big data in healthcare, and this is no exception to organ transplant. This figure shows the number of organ transplants in US from the year 1988 to the year 2020. You can see steady increase in almost every type of major solid organ. And you can imagine for every transplant recipient, we can further collect a myriad of data ranging from lab tests, imaging, and molecular data to data collect from even from wearable devices or even from social media to understand patients' health lifestyles. And traditional statistical learning methods will find a hard time to effectively analyze such massive amount of heterogeneous data sources. But with proper annotations, this big data can be well fueling some of the real exciting AI models. And this is exactly what's happening in the research field. This figure shows the number of publications about various solid organs transplant in PubMed, illustrating the popularity of organ transplant research with AI. All right, last, let's look at the B section, business, by asking two questions. Why AI for organ transplant and what AI can do for it? So first of all, it is necessary to understand why this is an important area. So organ transplant is an ultimate treatment for many end-stage organ failures. And clearly throughout the transplant journeys or jurisdictions, there's a significant disparity between the organ demand and donor organ supplies. Another reason this area is important is that we think organ transplant is a paradigm for the use of scarce health resources, including the use of limited organ donations or the use of intensive care beds during pandemic. Therefore, any tools that can improve any parts of the transplant journey for patients and healthcare professionals are important. But why is organ transplant difficult and a complicated area? First of all, it involves multidimensional donor and recipient space in which many factors such as sex, ethnicity, genetics, environmental exposures, lifestyles, BMI, diabetes, immunosuppression, you name it, all these factors play big roles. And many clinical factors have nonlinear interactions with the outcome. And people need to consider counterfactuals that you didn't just consider what the outcomes are if you transplant, but you also need to consider what the outcomes are if you don't transplant and what the outcomes are for those who don't receive the transplant. There's also literature highlighting the significant assignment bias and also informative censoring, which have lots of ethics implications. All of these add layers of complexity for the organ transplant. So you may wonder, what can AI do to help? To answer this question, I will walk you through a common trajectory for organ transplant recipient. Patients require an organ transplant are a complex population. Their journey includes pre-transplant evaluation and preparation, and also the identification of a suitable donor, and the transplant surgery, followed by post-transplant lifelong monitoring. And all of these journeys are managed by a multidisciplinary team of healthcare professions. And this is certainly an extremely simplified scenario, which already sheds light on some of the opportunity for AI applications. For example, we can apply AI for a predictive modeling of transplant suitability, whether this patient is suitable for transplantation. We can also use AI to help organ assessment and repair, which we're going to talk about as a use case in this talk. We can also have AI to help with donor and recipient matching and waitlist prioritization. We can also use AI for outcome predictions and resource allocations. Because of the large availability of EHRs and wearable device now, we can also use AI to analyze EHR data and wearable data analysis. We can also have AI to have a predictive modeling of long-term survival probabilities for risk stratifications, which also is one of the use case I'm going to talk about in this talk. All right, so hopefully now through the 4 elements, you're a little bit convinced that we can do something using AI for organ transplant. And next, I will walk you through 2 use cases as a proof of concept to at least convince you that we can actually do something using AI to help organ transplant. All right, the first use case I will talk about is to use artificial intelligence for advanced organ assessment during ex vivo lung perfusions. So the background of this project is 2 burning issues of lung transplant. The first is a shortage of donor lungs. This figure shows that while the total lung transplant, including single and double lungs, increase every year, but the rates of lung donations for the past few years have only matched the growth at population growth rate, and it creates a significant disparity between demand and supply. And what makes this even worse is that is the underutilization problem, that only 20% of, more or less 20% of the donor lungs are utilized, which has the least utilization rates among many other solid organs. Among the almost 80% of the donor lungs that are rejected for transplant, many may have been suitable. They are rejected because of multiple reasons, including lack of expertise, lack of subjective assessment system for lung qualities, and so on. Before we dive into the project details, I want to show some historical links between lung transplantation and Toronto, which makes me quite proud when I work with some of the top doctors in Toronto on this project. For example, the world's first successful single lung happened in Toronto, and also the first successful double lung transplant was also performed in Toronto in 1986. And at the University of Health Network, UHN, more than 200 lung transplants are performed every year. This is the largest lung transplant program in the world. And also at the University Health Network, the lung transplant team led by Dr. Chef Keshavi has pioneered ex vivo lung perfusion, or EVLP for short. EVLP is a transformative technology that is now the gold standard for donor organ assessment prior to lung transplantation. EVLP preserves donor lungs at 37 degrees of body temperatures and provides critical support that allows donor lungs to function normally outside of the body for up to 12 hours. So EVLP really enables objective physiology assessment and informed clinical decision-making prior to lung transplantation. And this figure shows that EVLP has resulted in more lung transplant and a lot more lives saved, although the number of EVLP transplant has decreased a little bit during pandemic because of the pandemic restrictions. All right, so this is a video Chef showed to me on our first meeting, and I think I should share with everyone too. Through this video, you can see that EVLP system keeps donor organs alive outside of the body and allows the surgeon to examine and treat the organ before transplant. It is not a common type of video you see on an AI talk, I know, but I was quite amazed when I first saw it. Of course, different people have different thinking when they see this video. Doctors may be amazed by how sophisticated this system is to keep lung alive. But when I would see this video as a data scientist, what happened in my mind was this. I was thinking, wow, that's a lot of data can be generated during every breathing cycle of the lung. And this is exactly true. So today, EVLP is a complex diagnostic and therapeutic platform that generates enormous amounts of valuable, and previously inaccessible clinical data, including the ability to record all the biochemical, biological, physiologic data, and also even imaging data. And the Shaft's team has really paid attention in data collections and curation. So we have a multidimensional and longitudinal data well managed for over almost 770 clinical EVLP cases in UHM for now. Despite these benefits, the decision-making process in proceeding to transplantation is not standardized. It is difficult to interpret the wealth of the information that EVLP provides in a timely manner, and it still requires experienced clinical judgment to consolidate the large data points. Therefore, to streamline the process, we have applied AI during EVLP to more accurately assess donor organs for transplant and predict recipient outcomes, which will ultimately revolutionize how we perform organ transplantation. We already developed a few predictive models that are foundational to the organ assessment. The AI model is termed as InsightTX model, and we're going to show some of the details about this model. Our InsightTX model uses a machine learning model called XGBoost, standing for Extreme Gradient Boosting. It is a machine learning algorithm that comprises an ensemble of decision trees in a gradient boosting framework. In addition to its easy interpretability, because it's a random tree-based method, it also has high efficiency and also ability to handle missing values. And this algorithm holds the potential for many state-of-the-art applications in healthcare. Currently, our model uses physiology data, biological data, and some of the biochemical data as well. And these data are collected in a longitudinal manner, and to predict first the decision to accept or decline the donor lungs for transplant, and second, to predict post-transplant outcomes, specifically the length of time a patient will require mechanical ventilations. To develop our model, we consider all clinical EVLP cases from the year 2008 to the year 2020, and excluded some of the EVLP cases that went from a double lung to single lung transplant and retransplant cases. So these resulted in 500 EVLP cases in our training data and almost 100 EVLP for our test data set. We specifically split the training and test in a temporal manner that we only take cases in the year 2008 to 2019 as training, and using the cases from 2019 to 2020 as test, because we want to test the generalizations of our machine learning model to cases in different years. So, and also as I mentioned before, the outcomes we want to predict can be roughly categorized into 3 outcomes. The first one is extubated within less than 3 days post-transplant. And also the second outcome is extubated more than 3 days, which is a relatively worse outcomes. And certainly we also predict whether this lung is unsuitable for transplantations. In total, the model uses 4 donor features and 26 clinical parameters extracted from biochemical, biological, and physiological parameters during EVLP. And because we can monitor the lung data in a longitudinal manner, for each assessment parameter, we extract 4 features from the longitudinal data: the minimum, the maximum value, and the last known value, and the trend over time, for a total of 108 input variables. People may wonder, can you take the whole time series data? The answer is yes, but as a proof of concept, the first experiment we did is to extract the 4 statistics from these 4-hour monitoring data sets. All right, so this is the result of our model. So in the training data set, the overall AU, the accuracy under the curve score was 79%. We then validated the model using the test set and observed a consistent level of performance compared to the training data. And thus, our proof of concept inside TX model is robust and will form a strong foundation for the more advanced AI models proposed in this project. And so we also perform reverse engineering by trying open the black box. As everyone knows that many people treat AI model as black box, but luckily this model inside X has some inherent interpretability abilities. So we look at the important variables for each outcomes, and we find we list the top 10 variables for each outcomes, which is listed here. And certainly I know very little about these variables, but through collaborations with all the clinical teams in SHAFT's, clinical professionals in SHAFT's team, they confirm that these top 10 variables for each outcomes make total sense to them. And some of the conclusions we can achieve by looking at these top variables for each outcomes is that physiological assessments were important features driving the prediction of short time to extubation and lung suitabilities, whereas biological and biochemical features were important predictors of prolonged ventilations. So after developing our model, we will develop, we are working now with Microsoft to develop a user-friendly software platforms that displays the algorithmic results in an easy to read format for the transplant teams. We not just stop at papers or stop at POCs, we want to push the AI model further into clinic. So to work with UHN Toronto lung transplant programs, and including a dedicated computer programmer who developed our current database software, and also the whole team will assist in developing a compatible program for showing the results of our AI models. So the dashboard we will develop is showing in this slide. The dashboard will include results from our inside TX model displayed as a predicted probability of the 3 outcomes we mentioned before. And also we will, to help compare with previous Toronto lung score inflation profiles, we're gonna show the previous score as well to display really as many informations to the clinicians to help them make the informed decisions. So here you will notice that we didn't let the AI to dominate the decision-making process by the clinic. Instead, we're trying to display as many information as possible to the clinicians so that they can make the most informed decisions. And also we will basically showing first of all, showing the inside TX model results, and also showing the traditional Toronto score, which are widely used previously by the lung transplant programs. And also, in addition, we show some cytokine informations to help clinicians understand better about the lungs quality, so that by combining all the information you can possibly gather, the clinician can make the most informed decisions. Certainly, we hope these AI models can have a transformative impact on a wide range of stakeholders. So hopefully our inside TX model will standardize the donor organ assessments around the world to help clinicians to make accurate and objective decisions regarding transplant suitability. Further, the model will greatly expand the donor organ pool and ensure that every patient in need of the transplant will receive one, with vastly improved quality of life. And finally, the project will result in operational and financial cost saving and optimize resource utilizations in hospitals. That's a future we hope to achieve through this project. All right, so the first case study is an AI tool that can help quality assessment and outcome predictions pre-transplant. And now next, I want to provide you another case study that uses state-of-the-art AI models for long-term mortality predictions after transplant for liver transplantations. So this study is a collaborative work between my lab and Dr. Mohammed Sabah. it has been recently published in journal Lancet Digital Health. The key features of this study are following. First, it is one of the first attempts that use deep learning algorithm to predict mortality in liver transplant by incorporating longitudinal follow-up data. Second, the model is able to make a more personalized risk calculator for managing long-term transplant care by categorizing each patient into a few major risk categories, such as graft failure or cardiovascular events. So as we all know now, in order to train machine learning models, you always need the first thing you do is collect data, all right? So we did the same thing for this project as well. To train the model, we have selected more than 65,000 liver transplant recipients in US between the year 2002 and 2014. These data are collected from the largest transplant database called Scientific Registry of Transplant Recipients, SRTR for short. And it is the largest transplant database in US. And thanks to the huge database, we are able to carve out a deeply characterized cohort with more than 200 clinical variables. And we model 5 major causes of death at both 1 year and 5 year outlooks. So we frame this project as a supervised classification problem. And we train 5 models, including logistic regression, which is one of the commonly used statistical learning algorithms so far, and also many other deep learning based models, such as recurrent neural networks, which we just briefly talked about previously in the A section, the algorithm section of AI, which is widely used to model longitudinal data. And also we used a recent state-of-the-art model called transformers. This model is being widely used in natural language processing to help people understand languages. It is also a deep learning model that can model longitudinal sequential data sets. We consistently find that deep learning algorithms usually outperform logistic regression by a large margin. And the best deep learning model to this longitudinal data set is a model called transformer I just mentioned. And because of the power of transformer in modeling sequential data set, and because of also the benefits of large amount of data set from SRTR, transformer can achieve the state-of-the-art accuracy of predicting 1 year probability of survival at the AUC of 0.81, and also the 5-year, the longer term outcome of survival at the accuracy of 74. And in contrast, traditional statistical learning methods such as logistic regression, the AUC for 1 year outlook is only 71%, and the 5-year outlook is only 65%. So you can see the advantage of more powerful deep learning models such as recurrent neural networks, such as transformers, in modeling longitudinal data at the base of big data. We also want to provide a certain amount of interpretability by opening the black box and trying to pick into the model, see which variables are important to make the accurate predictions. So this is exactly what we did. So we did the following 2 things. First, we trying to validate the model at the local database, which we collected a private data set from University Health Network to cross-validate the effectiveness of the model we trained from US. We want to see how generalizable the model we trained from US to patients we collected from Canada. And we find that the model consistently perform very well on Canadian data as well. So the accuracy on 1 year outlook and 5-year outlook are relatively consistent with the accuracy on the US dataset. And further, as I mentioned, to open the black box a little bit to help clinicians understand better about the model, we select the top 10 models from from the model trend in US, also from the model trend in UHN. Although we find slight difference of the top 10 selected variables across US and Canada, which is understandable. We also see some common variables, common important factors across US and Canada. So how does this study benefit the clinicians? As a follow-up, we are working to generate, a dashboard that enables a visual display of the personalized risk estimations of major mortality types, such as graft failures at both 1 year and 5 year. A prototype is shown here on the right. With these personalized risk calculators, we can help clinicians get an updated 1 year and 5 year probability of each outcome at every follow-up. For example, if a patient is flagged by the model with a high probability of cardiovascular related deaths, the clinician may need to send the patient to a cardiologist for a more thorough review. So hopefully with the dashboard, with the AI models, we can help clinicians better manage patients to have a better quality of life post-transplant. All right, so finishing the 2 case studies, hopefully now you are a little bit more convinced that AI can actually play a bigger role in helping either predicting the outcomes or helping managing patients post-transplant to improve their quality of lives. I want to also use the last few minutes to talk about some of the current limitations and challenges in applying AI in organ transplant research. Although it is quite promising field, as we talk about some of the use cases, it still suffers from 2 major challenges. I summarize as data challenge and also algorithmic challenge. Excuse me. All right, so first, data challenge. It is still very hard for computer scientists to gain access to transplant data. Most of the transplant research data are still in silo, and you need many rounds of requests and approvals in order to have access to these data sets. So if we plot the horizontal axis as the richness of the data you have access to, and the vertical axis shows the sample size of the data set you can have access. So the X is the richness, the Y-axis is the largeness of the data set. And most of the transplant data lies here, where the data sits in individual researchers' desktop with small sample size, and most of the data is on single modality, either imaging or clinical variable only. And SRTR, which we used in some of the previous case studies, the largest public registry data set from US is here with a large sample size, but only has administrative data without any other important modalities such as imaging, molecular data. And sometimes, if you're lucky, you can get data with quite rich representations, small sample size. Right? This we also showed some of the, for example, in the lung transplant project, we have access to very rich data set. That's because I'm extremely lucky to work with some of the top clinicians in this field. But many times when we access local data, we usually have a relatively lower number of samples, although the data representation is quite rich, ranging from different modalities, such as clinical variables, such as imaging, even sometimes molecular data. And certainly this is where we desire, right? We want to, in order to have show better power of AI models, we want to have a rich data set with large number of samples. And this is what we really desire, but in reality, it's really hard to get here. Another data challenge is data bias. So it is no secret that even SRTR, which provides the largest collection of organ transplant data in US, the data within SRTR contains bias in many aspects. For example, this figure shows a significant gender disparity in liver transplant recipients, that women have a significant lower rates in receiving liver transplant but has a higher waitlist mortality than men. Another example of bias is that within SRTR, we see a significant race disparity in receiving preemptive kidney transplants in both pre and post kidney allocation system. Because of this inherent bias in the dataset, we need to be alert when we train AI models on this data. A necessary step in dealing with data bias is rigorous validations, both retrospectively and prospectively for different populations. Another data challenge lies in data curation. This figure from Economics, a magazine, shows that more than 80% of the time and efforts are devoted to data access and to data curations. And this is very true for AI projects in transplant research. Very often, as data scientists, we spend quite a significant amount of time and efforts in making sure the data is correctly curated. There's not many missing data, and we have a consistent way to quality control and imputing data sets with missing modalities. Okay, another type of challenges we often face lies in the algorithms we use in AI so far. Many AI algorithms are considered as black box due to its massive number of parameters. This cartoon I will show here demonstrates the daily life of my research in my lab. Many times, my clinician collaborators, such as Chef or Momasa, would come to me and ask me, this is your machine learning research? This is your machine learning system? And I would say, yep. You pour the data into this big pile of linear algebra, and then you collect the answers on the other side. And the collaborator may ask, what if the answers are wrong? And I would respond, just stir the pile again until they start to look right. Right, this clearly shows the difficulty we have when we train complicated deep machine learning models, particularly deep learning models, because of its inherent difficulty in interpreting the models. So sometimes it's hard for us to explain why and what the model is looking at and how the model is generating such predictions. So this clearly has issues, although particularly on the AI acceptability. So although patients across the world are open to receiving AI-enabled healthcare, according to a survey in 2016, when it comes to organ transplant, which is a very specialized field, we really need to put AI on the hands of doctors. The lack of interpretability is particularly problematic since AI can only have an impact when it helps doctors arrive at a better decision than they would without the AI. They must be adjusting their decisions, right? If the AI recommendation always aligns with what doctors would do anyway, or what doctors are already doing, outcomes are no different than they would be otherwise. Thus, incorporating AI recommendations, often without interpretive explanations for where the recommendation is coming from, into clinical decisions is really a new skill for which there are no guidelines or textbooks. Right? This is definitely a challenge for us to increase the AI acceptability for doctors. All right, so I will use the last 1 or 2 minutes to look at the future work. So far, I've talked about many use cases to apply machine learning to single modality of patient, either clinical variables most of the time, or images or genomics. But in my mind, the future of AI in organ transplant should focus on multimodal approach, where you will take multiple modalities of patient data, such as image, such as ECGs, such as physiology images, physiology signals, or genomic data all together, and put this into a unified deep learning system and try to learn the signals between these data modalities and make the most accurate predictions. All right, so here I summarize the 4 key takeaways. First of all, AI and machine learning is gaining popularity in transplant research for effective pattern analysis from large-scale noisy data. And second, combined with AI combined with EVLP system can provide accurate assessment of donor lungs and predict transplant outcomes. And third, AI can enable accurate predictions of long-term mortality by learning from longitudinal follow-up data post-transplant. And last, AI in transplantation research is still in its infancy due to some of the limitations, including both data and algorithmic challenges. I want to acknowledge all the amazing help and efforts by my collaborators, particularly people from Chef's team, Chef Andrew and Bonnie in the EVLP project, and also Momasa and Amir for the liver post-transplant research project. And certainly all the credits goes to all the amazing students in my lab. They did most of the work. I'm just the one who talk here. Okay, I promise you, this is the last slide. So last, I want to conclude the talk by emphasizing that AI applications in organ transplant are still scarce and face lots of challenges, although it promises many transformative opportunities. The most challenging, but also most exciting part about it is it really takes a village to achieve. No single profession can achieve such a complex system without a multidisciplinary expertise ranging from computer scientists to clinician, or also health IT, human factors, and even regulatory experts. A successful AI project or product in organ transplant is like a child who needs a champion, or two, or three, or even more. Thanks for listening and happy to take any questions.
Awesome. Sorry you can't hear any applause, but I'm sure there would be tons right now. I'm sure people are clapping in quiet rooms everywhere. So we have quite a few questions, so I'll try and get through these very quickly. One very easy one, are there any opportunities in your lab right now for MNG or PhD or anything like that?
Yes, that's the answer is always yes. Yeah, please
Okay.
feel free to reach out to me.
All right, awesome. So done, answered that. So first question from Lucas, I think, is talking about your validation strategy of holding out future data from future years. Are there any particular advantages or disadvantages you could build on in that approach, and maybe talk about why you picked it in particular?
Yeah, that's a great question. So many times when we train AI in machine learning, we see some kind of label leaky phenomena where, because most of the data set we use for AI are collected retrospectively, right? What many people do is that they split 80% of the data and 20% of the data, and 20% data as test, all right? And many often training tests share the same distributions. And therefore, you kind of see inflated accuracy numbers on the test data set. So, but this is just really inflated numbers. We want to see the reality of the AI models. So that's what we did in the EVLP project. We purposely split the data into training that is from previous year and test on the future years, just to validate how generalizable the AI model is. Because at the end of the day, we want to use the AI on future data, right? On data we never seen before. So that's really the purpose of that design. Certainly there's challenges with that, right? Because of, you never know what will happen in future years. And because of something that you never expect may change the distributions of noise, of signals in your future data, right? But we believe that that's the reality. And we want to face that. We want to test how accurate the model is in reality.
Yeah. Maybe a quick clarification. The two sort of case studies you had, they were completely separate. You didn't share any models or training with them, right?
They're completely separate because
it's an organ. Yeah. Okay. So so our next question is really around additional data which you could use in the model. So it seems, and you can correct this if this is wrong, that you only use data collected from the lung itself, and you didn't use any data from the recipient. So there are two individuals who are just wondering whether adding in information from the recipient themselves is a direction that you're thinking about going.
That's excellent, excellent. Exactly, that's the project on the EVLP I presented is really the first step, right? We want to really as a POC, because nobody has ever applied AI on EVLP data. So that's the first step. So next step is including more modalities such as X-ray images, such as genomic data, and also including recipient data is a natural extension of our project in next phase.
Yeah, okay. Yeah, and there was a little bit of a question of whether this works. Did any of your clinical collaborators speak to why using only data from the donor lung was sufficient to capture organ transplantation success?
Yeah, that's a good question. So some of the explanations I learned is that good lungs generally have higher probability of successful transplant. And also EVLP can really provide a holistic view about the lung quality before the transplant. So the idea is that if the lung is generally good, it will generally have higher probability of success, right? And the current, as I mentioned, the current challenge of lung transplantation is underutilization problem. Only 20% of the donated lung are transplanted. So we want to improve that underutilization problem by only look at the lung qualities.
Yeah, I mean, I might go off script here and kind of build on this. How do you foresee your model, which has been trained only with past successes, will be able to expand the sort of donation pool by potentially considering lungs, which would have been viable, but yeah, only considered viable by your algorithm or something like that? Like, is that the kind of aim?
Yeah, excellent question. So excellent point. So in my understanding is that all the data we are working on are collected based on the expertise that is top doctors in the world, right? They are managed by Chef's team, and these are really top doctors in the world when it comes to lung transplant. And we want the AI model to learn this experience from these top doctors. So hopefully we can disseminate the knowledge AI learned from these top doctors to other hospitals where the expertise may be less, and hopefully they can, by consulting the AI models, they can increase the utilization rate of lung donations.
Cool.
We really just want to learn.
Yeah.
In other words, we want the AI to learn from chefs.
Makes sense. Yeah, so we still have a few more questions which we'll try to get through all of them. Do you have any sort of suggestions on just how to improve the AI adoption among clinicians, or what has been successful in sort of your experience?
Yeah, that's an excellent question. So I think there are many aspects we can work on to improve the AI adoptions. One is education, right? So hopefully, T-CAIREM is one of the institutions that is based on this aim, right? We want to really educate all the clinicians who are really smart and open to new ideas to know more about the opportunities and also limits of AI exams, so that they understand AI and they don't think AI is some kind of magic or a mystery, right? So they are more accessible to AI exams. The second one is on the data scientist side, right? We need to really work with clinicians to help them to showcase the power of AI, and also trying to do better job in demystify machine learning and interpret the machine learning models to doctors to fit into their clinical perspectives, right? So I think the key is really collaboration. As I mentioned in the last slide, it takes a village. We really need collaborations and communications between different sides to improve the improve the AI acceptability and AI adoptions in clinic.
Yeah, makes sense. And then they had a second very quick question about the long-term outcome data or the longitudinal data. Did you do any NLP to pull that out, or was it available in a structured form?
Could you say it again? I think you
so the data which you used for sort of longitudinal outcomes, was that collected in a structured form as a part of this registry, or did you have to do any NLP?
Yeah, that's an excellent question. So the data curation are mostly done by my collaborators team, Moyasa's team. So they did a great job in curating some of the clinical variables for us. So if I understand correctly, we didn't use any fancy NLP to curate this. So the SRTR data already are relatively well structured.
But originally they did parse it from a note, for example. Yeah. Okay. So we had some human NLP in the loop. Great. So then the next question is sort of about how to deal with an incomplete overlap of variables between the training and test sets, and especially with multi-center data.
Right.
Just sort of how to handle that and handle, missingness levels.
Yeah, that's an excellent question. So these are really like all the details, like the devil lies in the details, right? So I didn't mention too much about this one, but yes, this is a common phenomenon. We see that many times we don't see overlapped variables across different centers because different centers use different standardizations, right? So this is also the case on the liver transplant data set, where we see only a subset of overlapped variables between US data and Canadian data. So what we did is we train a model on US data. We only take the part of the architecture that is associated with the overlapped variables and use that to transfer, to perform transfer learning to UHN data. For the variables that are not overlapped with US, we have to train from scratch, right? But hopefully that's kind of part of the data challenge I was mentioning, right? So ideally we should have all the same standardization of data curation across the world so that we can best benefit the AI models. But in reality, we never have that. So what we can do is really do what we can to fine tune the model to transfer learning from the US model to Canadian model. But for the variable that is not overlapping, we have to train from scratch.
Yeah, that makes sense. And then there's a suggestion to think about collaboration with regenerating labs like Golands and Eric Chadwick. So I'll
yes,
say
always,
it's a good suggestion. Yes. And then I guess it's actually 1 p.m. so we don't have any more time to answer any questions, which is a shame because there are some good ones here. But I will take this opportunity to say thank you again, Bo, for that talk. That was super interesting, and it's a great application of some of the new techniques. Thanks everyone for attending. If you want to hear about more of these talks, then follow us on Twitter, UFT_T-CAIREM, or subscribe to the mailing list that comes out every month that always has some interesting interviews with faculty in the area doing AI and whatnot. Otherwise, thanks so much for your attendance. Thanks again, Bo, for the great talk, and I'll see you all around.
Thank you for listening. Have a good day. Bye-bye.